All right, diffusion of gases. This is about as straightforward as it gets. This should sound very much like physics because it's just objects moving. Now, with diffusion of gases, we have two terms that we need to know. Diffusion, which is the random scattering of gas particles from high concentration to low concentration, and effusion, the movement of particles through small holes or pores. Now, these two we can use almost interchangeably because if something diffuses faster, it will effuse faster relative to something else. The same factors affect both of them. Now, generally speaking, of course, effusion is slower than diffusion because it has to make it through some kind of a porous membrane. But again, everything that applies to diffusion also applies to effusion. Now, rates can vary depending on a whole bunch of things. Temperature, of course, because that's the average kinetic energy. Temperature goes up, things move faster. But mainly, we're going to look at one idea. And this is the predominant idea. If all the conditions are the same, if I am comparing two gases, the heavier particles will diffuse more slowly than the lighter particles. Makes sense. Same amount of energy, lighter particle is going to move a lot faster than the heavier particle. Now that brings us to Graham's law. And this relationship is not as simple as you would think. It's not simply an inverse relationship between mass and velocity or rate of diffusion. What we've got is this. The relative rates at which two gases at the same temperature and pressure will diffuse vary inversely as the square roots of the molecular masses of the gases. I mean, obviously. Or, as I like to put it, like this. Now, this derives from the kinetic energy equation, where kinetic energy is mass times velocity squared. So when you're trying to get that by itself, you square root it, so you end up with just velocity, and you end up with square root of mass. And it's, of course, an inverse relationship, so V1 over V2, M2 over M1. So it's all there, but from here, it's just a matter of algebra. So if I know the molecular mass of one gas, the molecular mass of the second, if I know the velocity of the first gas, I can calculate or solve for what the velocity of the second gas will be. Likewise, we can use that velocity to identify gases. Yeah, we're doing that again. So if I have a known gas and I have it under the same conditions, I can compare its rate of diffusion to an unknown gas. And based on that ratio, I can find the mass of the unknown gas. So we're going to start off with a fairly simple, straightforward one. Just kind of plug and solve. So pause for a couple of minutes. Work this through in your notes. When you're done, restart. All right, so here we go. We have our equation. We're given the rate of diffusion of helium. We know the mass of helium from the periodic table. And I want to know what would be the rate of diffusion of oxygen under the same conditions. So O2, now helium, obviously not diatomic, it's a noble gas. We solve for the V2. Now notice here, what happens when you divide the grams per mole, the units cancel out. That square root of 8, that is a unitless number. We solve, and boom, 15.9 centimeters per second. So pretty straightforward. Now our next example is we have helium again. We have its rate of diffusion. We have an unknown gas and its rate of diffusion. And we want to find the molar mass of the unknown gas. Once we solve for that, see what is the unknown gas. So again, pause for a moment, solve it out, figure it out, restart. All right, solving here. Now notice that ratio of the rates ends up being 3.21 or 3.2121. Now, we need to square both sides of the equation to get rid of the square root. So on the right side, it just cancels out the square root. On the left side, it actually squares it. Now, solving, we have 41.2 grams per mole. And now it's a matter of finding a gas that's going to have that molecular mass. And that is pretty darn close to argon. You know, you could try getting a diatomic out of that and just try different combinations, see what works. The closest gas that we would expect is going to be argon. All right. Now there's this one. Now this one, it's asking a different question. And this is seeing how comfortable you are with the math. Because we're trying to get the ratio excuse me, of the rates of diffusion of carbon dioxide to carbon monoxide. Now that is a very specific, basically you're getting the fraction of the rate of carbon dioxide to the rate of carbon monoxide. You do not need to find either one of those because, the left side of our equation, the left side of Graham's law, is going to basically cover that. So the carbon monoxide is going to diffuse faster simply because it's lighter. That is a quick kind of inspection notice. And what you're solving for is that ratio, what's in the red box there. So put in the numbers, solve it out, take a minute. All right, so now we put in the numbers for the masses, and it honestly does not matter what the conditions are. As long as we have the same conditions, the velocity of carbon dioxide is going to be 0.7978 times the velocity of carbon monoxide. And there's several ways you can express that. You could say that what I just said, carbon dioxide, its velocity is 0.7978 times carbon monoxide. You could say that the velocity of carbon dioxide is 79.78% of the velocity of carbon monoxide. Whatever floats your boat.